Suppose these are atomic orbitals 1s, 2s, 2p, and another same set of atomic orbitals 1s, 2s, 2p. So molecular orbitals formed will be 1s, 1s. This will form sigma 1s, sigma star 1s. Similarly, 2s, 2s, that is sigma 2s, that is BMO, and sigma star 2s, that is ABMO. Not 2p, 2p. Suppose Z axis is the internuclear axis. So 2pz, 2pz will form sigma 2pz and sigma star 2pz. Then 2px, 2px, 2py, 2py will form pi 2px equal to pi 2py. These three BMO and these three ABMO, that is pi star 2px equal to pi star 2py, and then sigma star 2pz. This is the molecular orbitals for homodiatomic molecules. Because in case of homodiatomic molecules, both atoms will be same, so energy of same orbitals of both atoms will be the same. This is the increasing energy of molecular orbitals for the molecular species up after N2, that is for O2, F2, Ne2, etc. And here you can see pi 2px and pi 2py are degenerate molecular orbitals. Degenerate molecular orbitals means molecular orbitals having the same energy. And similarly, pi star 2px and pi star 2py are degenerate molecular orbitals having the same energy. And in case of degenerate molecular orbitals, Hund's rule will be applied. That is, if two electrons enter here, then first we will fill 1 1 and then pairing will start, right? That is according to Hund's rule, filling of electron will take place. This is the molecular orbitals in their increasing energy for the molecular species after N2, that is for O2, F2, etc. Right? For example, if you have to write the MOT, that is molecular orbital theory, that is a structure by MOT for O2, then this order of increasing energy of molecular orbitals will be followed. And as you know, in O2 there are total 8 2 just 16 electrons. So 2 2 2 2 1 1, then pairing here 2 2 2 2 2 2 2 14. Now 2 electrons should go into this, but degenerate molecular orbitals, so 1 1 according to Hund's rule. And therefore you can see in O2 there are 2 unpaired electrons, and so O2 is always paramagnetic. Now for molecular species up to N2, that is for B2, C2 and N2, the increasing order of molecular orbitals is as first sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, and after sigma star 2s, electron will go into pi 2 px equal to pi 2 py, then in sigma 2 pz, then pi star 2 px equal to pi star 2 py, and in last sigma star 2 pz, because here z axis has been taken, the internuclear axis. Now you can see here up to the molecular species, for the molecular species up to N2, that is for B2, C2 and N2, the energy of sigma 2pz is higher than the energy of pi 2p. But for the molecular species after N2, that is for O2, F2, etc., the energy of sigma 2p is lesser than the energy of pi 2p. So remember this point here. For the molecular species up to N2, that is for B2, C2 and N2, the energy of sigma 2p becomes higher than the energy of pi 2p, and this is due to sp mixing. This is due to sp mixing. So you can write here, for the molecular species up to N2, that is the molecular species having up to 14 electrons, that is for B2, C2 and N2, the energy of sigma 2p becomes higher than the energy of pi 2p, and this is due to sp mixing in them. But for the molecular species after N2, that is for O2, F2, etc., the energy of sigma 2p is lesser than the energy of pi 2p. That means no sp mixing in them. So here it becomes clear that due to sp mixing, the energy of sigma 2p becomes higher than the energy of pi 2p. This becomes very much clear here. Due to sp mixing, the energy of sigma 2p becomes higher than the energy of pi 2p. You must remember this. Now here one question arises here. Why up to N2 sp mixing occurs and after N2 sp mixing does not occur? So from a spectroscopical data, it is observed that for the elements up to N, that is up to nitrogen atom, that is for boron atom, carbon atom and in nitrogen atom, it is seen that the energy gap in between 2s and 2p is small. And if energy gap in between 2s and 2p is small, then there will be some mixing in between 2s and 2p, and this is called sp mixing. But after the elements N, that is in case of atoms O, F, etc., by a spectroscopical data we see that the energy difference in between 2s and 2p is large, and therefore no sp mixing occurs in 2s and 2p after the elements, and that is in case of O, F, etc. Now, why up to the elements N sp mixing occurs and after N, that is in OF, sp mixing does not occur? Listen. Up to the elements N, that is in boron, carbon and nitrogen, you see that in boron there is 2p1 in the last shell, in carbon there is 2p2 in last shell, and in nitrogen there is 2p3. That is, p orbitals are singly filled, no pairing of electron in p orbital is there. But after N, that is in O, it becomes 2p4. That is, in 2p4 in O, one p orbital has 2 electrons, and if in an orbital there are 2 electrons, there will be mutual repulsion between 2 electrons in one orbital, and due to this mutual repulsion between 2 electrons, the energy of 2p becomes higher. Listen, the size of atom decreases on moving from left to right in a period. So the energy of 2s decreases regularly, but after N, that is from O, the energy of 2p becomes higher due to pairing of electron in p orbitals, and therefore after the elements N, that is in O, F, etc., the energy gap in between 2s and 2p, that is energy of 2s decreases but energy of 2p increases, so energy gap in between 2s and 2p becomes very large, and therefore after N, that is in O, F, etc., no sp mixing takes place. And if no sp mixing takes place, then the energy of sigma 2p will be lesser than the energy of pi 2p. So remember this. What is sp mixing? This sp mixing is different from sp hybridization. In sp hybridization, both sp hybrid orbitals are equivalent, but in sp mixing, the orbitals having s and p character are not equivalent. One has more s, less p, and other has more p, less s character. So now, one point more here. Bond order, that is bond multiplicity in between two atoms. Bond order is calculated by using this formula: Nb minus Na upon 2. And here Nb is number of electrons in BMO and Na is number of electrons in ABMO. According to Mott, the bond order may be integer or fractional or positive or negative or zero, everything. Now, bond order is directly proportional to bond strength. So, bond order is directly proportional to bond energy, because if bond strength is more, then bond energy will be more, and therefore bond order is inversely proportional to the bond length. More bond order, lesser, smaller bond length. But remember here one thing: if two molecular species have the same bond order, if two molecular species have the same bond order, then more the number of electron in ABMO, lesser will be the bond strength and bond energy, and hence greater will be the bond length, because electron in ABMO increases the energy of the molecule and thus destabilize the molecule. So if two molecular species have the same bond order, then you will see number of electrons in ABMO. The molecular species in which ABMO has more number of electrons will be less stable, it will have less bond strength, less bond energy, and so greater bond length, right? Now look this, HOMO. The full form of HOMO is highest occupied molecular orbital. That is, the molecular orbital, the last molecular orbital which has electron is called HOMO. And LUMO, its full form is lowest unoccupied molecular orbital. That is, the vacant molecular orbital just after HOMO is called LUMO. And HOMO and LUMO are FMOs, that is frontier molecular orbitals. As in case of an atom, that is electronic structure by atomic orbitals, the valence shell electronic configuration decides the properties of the element. In the same way, in case of the molecules, you will write the structure by Mott, and here the frontier molecular orbitals, that is HOMO and LUMO, will decide most of the properties of the molecules. HOMO donates electron and LUMO accepts electron, and one is called SOMO. Full form of SOMO is singly occupied molecular orbital. If a molecular orbital has one electron only, then such molecular orbital is called SOMO. And SOMO is both HOMO as well as LUMO. Because if MO has one electron, then it can donate electron as well as it can accept electron also to pair the electron. So SOMO will be called both HOMO as well as LUMO. So here you must remember, bond order of a molecular species can be 0, positive, negative, integral, fractional, everything. Now, if bond order of a molecule comes to be 0, then such molecular species will not exist, right? So you may write down this: if bond order comes to be 0, then such molecular species does not exist. And similarly, if bond order is negative also, then such molecule will not exist. But if bond order is greater than 0, that is positive, then such molecular species will exist. And higher the bond order, more the bond energy, more the bond strength, and so more the thermodynamic stability of that molecule.